Hello, and welcome to the fifth section of this course, Simple Feed-Forward Neural Networks. The section will demonstrate the following topics: preliminary concepts of neural networks, neural network projects on nonlinear synthetic function regression, projects on predicting car fuel efficiency with nonlinear regression, learning to classify wines, and multi-class classification. Now, we will see the first video of Section 5, Preliminary Concepts. To build a simple framework into the neural network components and architectures, we will give a simple and straightforward build of the original concepts which paved the way to the current complex and varied neural network landscape. Artificial neurons. An artificial neuron is a mathematical function conceived as a model for a real biological neuron. Its main features are that it receives one or more inputs, training data, and sums them to produce an output. Additionally, the sums are normally weighted and the sum is passed to a nonlinear function. Original example: the perceptron. The perceptron is one of the simplest ways of implementing an artificial neuron, and it's an algorithm that dates back from the 1950s, first implemented in the 1960s. It is basically an algorithm that learns a binary classification function, which maps a real function with a single binary one. Perceptron Algorithm. The simplified algorithm for the perceptron is: Step 1. Initialize the weights with a random distribution. Step 2. Select an import vector and present it to the network. Step 3. Compute the output of y' of the network for the input vector specified and the values of the weights. Step 4. The function for a perceptron is: if y' not equal to y, modify all connections we by adding the changes delta w is equal yxi. Step 5. Return to Step 2. Neural network layers. The single-layer perception can be generalized to many layers connected to each other, but there is an issue remaining. The representing function is a linear combination of the inputs, and the perceptron being just a kind of linear classifier, there is no possibility of correctly fitting a nonlinear function. Neural network activation functions. The learning properties of a neural network would not be so great with only the help of a univariate linear classifier. Even some mildly complex problems in machine learning involve multiple nonlinear variables, so many variants were developed as replacements of the transfer functions of the perceptron. In order to represent nonlinear models, a number of different nonlinear functions can be used in the activation function. This implies changes in the way the neurons will react to changes in the input variables. The most common activation functions used in practice are Sigmoid, tanh, ReLU. Sigmoid, the canonical activation function, and has very good qualities for calculating probabilities in classification properties. Tanh, very similar to the sigmoid, but its value range is -1, 1, instead of 0, 1, ReLU. This is called a rectified linear unit, and one of its main advantages is that it is not affected by the vanishing gradients problem, which generally exists on the first layers of a network to tend to values of 0 or a tiny epsilon. Gradients and the backpropagation algorithm. When we described the learning phase of the perceptron, we described a stage in which the weights were adjusted proportionately according to the responsibility of a weight in the final error. In this complex network of neurons, the responsibility of the error will be distributed among all the functions applied to the data in the whole architecture. So once we have calculated the total error and we have the whole function applied to the original data, we must now try to adjust all variables in the equation to minimize it. What we need to know to be able to minimize this error, as the optimization field has studied, is the gradient of the loss function. Given that the data goes through many weights and transfer functions, the resulting compound function's gradient will have to be solved by the chain rule. Minimizing loss function gradient descent. Let's have a look at this graph to understand the loss function. Neural networks problem choice, classification versus regression. Neural networks can be used for regression problems and classification ones. The common architectural difference resides in the output layer. In order to be able to bring a real number-based result, no standardization function like Sigmoid should be applied. In this way, we won't be changing the outcomes of the variable to one of the many possible class values, getting a continuum of possible outcomes. TensorFlow activation functions. Most commonly used functions for TensorFlow navigation. tf.sigmoid x, the standard sigmoid function. tf.tanh x, hyperbolic tangent. tf.nn.relu, features, relu transfer function. Other functions for TensorFlow navigation. tf.nn.elu, features, computes exponential line REXP. tf.nn.softSign, features, computes softSign. tf.nn.bias_add value, bias, adds bias to value. TensorFlow loss optimization methods are described here. This is the original gradient descent method with only the learning rate parameter. This method adapts the learning rate to the frequency of the parameters, improving the efficiency of the minimum search for sparse parameters. This is a modified AdaGrad, which will restrict the accumulation of frequent parameters to a maximum window, so it takes into account a certain number of steps and not the whole parameter history. This method adds a factor when calculating gradients, corresponding to the average of the past gradients, equivalent to a momentum factor, thus the name ADAM from Adaptive Moment Estimation. Sklearn Preprocessing Utilities. Let's have a look at these Sklearn preprocessing utilities. Preprocessing.standard scalar normalization of datasets is a common requirement for many machine learning estimators, so in order to make convergence more straightforward, the dataset will have to be more like a standard normally distribution that is a Gaussian curve with zero mean and unit variance. In practice, we often ignore the shape of the distribution and just transform the data to center it by removing the mean value of each feature, then scale it by dividing non-constant features by their standard deviation. For this task, we use the standard scalar, which implements the tasks previously mentioned. It also stores the transforms in order to be able to reapply it to the testing set. Standard scalar.fit_transform simply fit the data to the required form. The standard scalar object will save the transform variables, so you'll be able to get the denormalized data back. Cross_validation.train_test_split. This method splits the dataset into train and test segments. We only need to provide the percentage of the dataset assigned to each stage. Nice! We've successfully learned about preliminary concepts.